Oh, okay.
Okay, so hi everyone. Today we have the pleasure to welcome Álvarez from the Universidad Complutense in Madrid and IPARCOS. And he will talk about quantum filaments, superradiance, and charged black holes. So please, thanks for being here.
Okay, of course, thank you very much for the invitation for giving the seminar. And I'm coming from Madrid, from Spain, where I'm finishing my PhD. Basically, I live in next one. And I'm going to present you a talk, a paper that I worked in collaboration with Elizabeth and Stanley at the University of Sheffield last year, in the state. And it's going to be about superradiance. Actually, quantum superradiance, okay? So first of all, my idea was to, first of all, I work on quantum field theories in curved space-time. So I'm very interested in the quantum effects, given that we have a strong gravitational background or a strong electromagnetic background. Here, in this example, we are going to discover that these both effects, both gravity and electromagnetic fields, play a very relevant role for quantum effects, okay? And they are both necessary for this. So let's give just a brief glimpse of what's to come, a brief idea, and then let's get into the details. But the idea is more or less easy, okay? So first of all, what is classical superradiance, or in general? People, when you talk about classical superradiance, they think about rotating black holes, scary black holes, and then everything is classical. What happens is that if you have some incident bosonic radiation, then you have more emitted radiation by the black hole due to a scattering process. So basically, you have more reflected radiation than the incident radiation that you have initially. Okay, so that's what in general is classical superradiance. And this happens with bosonic field waves. Okay, we are going to work here with fermionic fields, but let's talk about that later. The point is, okay, where the energy comes from, because obviously we cannot create energy from nowhere. So basically, what happens is that the black hole loses energy momentum and energy, so that it provides in the scattering process energy to the emitted radiation. Okay, so that's the general idea. Now, what happens is that if we study another setting, not rotating black holes, but charged black holes, what happens is that we can also have classical superradiance with bosonic radiation. Okay, and basically what happens now is that instead of losing energy momentum, of course, what it loses is charge and energy. And it leads to a similar process. Okay, so this is just everything is classical. What happens, and with bosonic fields, what happens if we consider fermionic fields? If we consider fermionic fields, what happens is that we do not have classical superradiance. We are going to look to understand why later. But then what we are going to ask is, okay, if we do not have a classical superradiance, do we have a quantum counterpart of this phenomenon? Do we have a quantum phenomenon that is quite similar to the classical counterpart? And our answer is going to be yes. And in this sense, we are going to find a purely quantum effect that doesn't have a classical counterpart. Okay, so and that's very interesting. The general idea, the physical idea is very, very simple. Charged black holes have an outer event horizon, and this event horizon, we have a region close to this event horizon that is called the effective ecosphere, in a similar way, in some sense, to the Kerr black holes, to the ecosphere of the Kerr black holes. And then that region, what we are going to have is pair creation. Particles and antiparticles that are going to be created and are going to be emitted. For example, if the black hole is positively charged, then there's going to be a negative inward flux that is going to be annihilating the charge of the positive black hole, charged black hole. Okay, and then this is going to lead to the discharge and the energy loss. So this is the general idea. We want to find a place, a region where we have particle creation, and then a loss of energy and charge. Okay, I didn't say that you can interrupt me whenever you want, of course. as many things. Perfect. So this is just the idea. Now let's get into the details. Okay, so for getting into the details, we are going to first just talk about classical things. Then let's come the quantum part. But for the classical aspect, let's present the ingredients of this recipe. And of course, the first ingredient is the background. Okay, the background, which is going to be a resonant neutron black hole, a charged black hole. There you have the metric. And for superradiance, we are only going to be interested in the outer part. I mean, a resonant neutron black hole has two horizons, an inner horizon and the event horizon, which is the outer one. And we are only going to be interested in the outer region of the outside the event horizon, okay? Because for superradiance, the black hole acts as a scattering potential, effectively. Okay, so basically we are going to be interested only in that part of the Penrose diagram that I draw here, only for R larger than R plus. Okay, so this is the Penrose diagram corresponding to that part, to the outer region. For the Penrose diagram, just say that, of course, the red part, which is the right part of the Penrose diagram, represents asymptotically far away from the horizon, and that means that we recover asymptotically Minkowski spacetime, no? Flat spacetime. So these are for large R's, and for R's going to the event horizon, this is just the curves that I draw in blue. Okay, and now obviously we have here with the minus the past, the asymptotic past, and the asymptotic future with the pluses. Okay, so this is the only ingredients that I really need to understand the core of this. So this is regarding space-time, and now we need to put on top of that a field, a fermionic field. Okay, so for the fermionic field, we are going to be interested in massless fermionic fields, just for simplicity, but everything is quite similar with well, some difference, but not the physics, actually. So what we are going to, for massive fields, I mean, I didn't know if I said the entire sentence. So basically, we have a massless fermionic field, but its dynamics is governed by the Dirac equation that is written over there. Okay, and now we have in that Dirac equation a vector potential for the electromagnetic field. Okay, and the vector potential, we fix a gauge, and the gauge that we fix is nothing but the gauge that conserves the spherical symmetry of our system and the staticity of our system. Okay, so basically there's a preferred gauge, which is the one that behaves as a gauge, as a Coulomb potential outside the black hole. Okay, so choosing that gauge, what we are interested now, and little q is the fermion charge. Okay, of course. So now what we are interested for understanding this and for also discovering and constructing the quantum theory is, let's look for separable solutions of this equation. Okay, so we are looking for solutions of this time. Of course, we have that exponential of minus I omega t because we have a static system and we have a characteristic frequency which is going to be omega. Okay, so that part is quite trivial and comes from the staticity of the resonant neutron black hole. Then we have there an e to the im phi because of the spherical symmetry, and we have there a 4-spinor composed by two 2-spinors. Each 2-spinor is written here, and it's a product of two different things. One that goes with the theta angle of spherical coordinates, and its dynamics, it's quite simple because it's just a generalization of this usual spherical harmonics, but for fermions, which are called spin-weighted spherical harmonics, but it's nothing interesting, it's just due to the spherical symmetry. What is interesting here is the radial behavior, which is of course the coordinate that suffers more from what's happening in the resonance from one. Okay, so that's where we are going to focus in the radial functions. Okay, and L is the chirality, but we are going to work with a fixed chirality, and everything can be generalized. Okay, just for simplicity. So now let's analyze the radial behavior, okay? I could have written here the equations of motion, but what I'm going to write here actually is just the solutions, how the behavior of these solutions of the radial functions behave in the resonance of black hole, okay? So, first of all, asymptotically far away from the horizon, which is the red wedge here, of course, what we find is what we expected. We want things to be quite similar to flat space-time. So what we recover is plane waves with the characteristic frequency omega that we found before. Okay, so basically, that's for the right side. Everything as Minkowski space-time. Okay, and I need to present. I'm sure that most of you are familiar with that coordinate, the tortoise coordinate, which is just a function of r. It's just an injective function of r, but which works better in these settings. And in the case that we go very close to the outer horizon, when r goes to r plus, r star goes to minus infinity. Okay, it's just a rescalation of r. So what happens if we get closer to the event horizon? Well, of course, inside that diagram, we have a potential. We have an effective potential due to the presence of a black hole, and that we do not have flat space-time. We have something there. So what happens is that the radial functions behave widely inside the square, but when we get close again to the event horizon, what happens is that r happens to behave again as a plane wave. But a plane wave, and this is very important for what follows, a plane wave not with frequency omega, but we have there another letter, which is omega tilde. And omega tilde is not omega, and this is essential for understanding everything. Omega tilde is not omega, but omega plus a shift. A shift that is given by the charge of the fermion field times the charge of the black hole divided by r plus. So the point here is that if we wouldn't have charge, if we didn't have that interaction between the charges, for example, if we put a scalar field in a sparse black hole, then that omega tilde would be equal to omega, okay? And then, and this is a spoiler, we wouldn't have super radiance, okay? Because it's very important that omega tilde is not equal to omega, okay? So that's the point until here. Any question or whatever? I mean, you can ask whatever you want. Another thing is that if I'm going to answer correctly, at least I'll try. Okay, so this is the behavior for the radial functions. Now, what we need, and it's going to be useful also for the quantum theory, is let's construct an orthonormal basis of solutions. And for that, let's analyze and let's pick different solutions for the radial equations, because the other ones are easy. Okay, so basically for that, what do we need? What do we need is to impose some initial conditions for the radial functions to solve the equations of motion. Okay, so let's analyze between among the infinity possibilities of choosing the radial functions. Let's pick some convenient, physically motivated solutions. Okay, so the solutions that we are interested in are the following. For example, the first one, the in-solutions. What do we call the in-solutions? The in-solutions are radial functions such that we have a unit. I think I'm going to use this to show you, because if not, I'm going to, oh no, yes. In a scry minus, we have a unit flux of radiation and nothing coming from H minus, okay? The Cauchy surface, because we have massless fields, is composed by H minus and scry minus, okay? So if we impose the initial behavior of the radial functions here, the in modes are basically those that behave as unit flux entering, from asymptotically far away from the horizon, and these modes enter, and what happens is that they become partly reflected because of the scattering process. It becomes partly reflected again to a scry plus, but partly transmitted into the horizon. Okay, so these are the in modes. The up modes behave in a similar way, but what happens now, because we need to provide values in the entire Cauchy surface. So the basis of solutions is composed by the in modes and the up modes. Okay, so basically in H minus, we have now a unit flux that is now going outwards from the horizon, but part of it is reflected and part of it is transmitted, okay? Transmitted now outside, I mean, asymptotically far away from the horizon, okay? So a basis of solutions is composed by in and up modes of this characteristic, okay? And the important thing here is we have reflected and transmitted radiation, as I previously said to you. Okay? Any questions or whatever?
There are things leading to horizon.
There are things?
Are there things leading to horizon?
I don't understand what you said.
The modes. They're leading from horizon to infinity.
Yeah, I mean, yeah, this one, for example. Yeah, I mean, this one is going from the event horizon, and the part that is transmitted outwards, I mean, asymptotically far away from the horizon, is that one, the transmitted one. That was your question?
Yeah.
Okay. And sorry?
It was just for
Perfect. And part of it is reflected again. And the same one happens to you. Okay? So that's the point. Now, why do we say that we do not have classical superiorities with fermions? Because you can quite easily, you can discover a relationship between the reflection coefficients and the transmission coefficients. And what you find classically is that the reflection coefficient is smaller than 1. And that means that you have less radiation than the incident radiation, than the unit flux that you were introducing after. Okay? So this is basically why we do not have classical superiorities. Okay? So that's it. Everything here until now has been classical. Okay? We do not have classical superiorities with fermions, but I said before that we did have classical superiorities with scalar.
So in case of the modes, the fact that R is smaller than 1 means that there's more things going out.
Yeah, no, because R could be very small, very smaller than 1, and we could have reflected radiation, but we wouldn't have a larger amount of radiation than the incident one, that is a unit flux. Okay, so the one is just basically because of the input that I'm giving. I mean, I'm setting in my black hole, I'm introducing a unit flux of radiation, and then if R is larger than 1, it means that I'm having more emitted radiation by the black hole than the incident radiation that I'm applying.
Well, this is clear to me in the in case, but for the other case, it wouldn't be that it would be bigger than 1, for instance, to a certain case.
Oh, I know what you're saying. No. I mean, R and T are larger than 1, because basically, I mean, everything is, yeah, maybe I understand what you're saying. Yeah, but the point is that the up modes, I mean, these form a basis, but actually what is interesting in what I'm saying is the in modes, are the in modes. Yeah, but indeed, because of this relationship, R and T are larger than 1. I mean, smaller than 1. Yeah, because of the exactly the same reason. I mean, you can. Okay, but yeah, I understand what you're saying. It's going to be useful for other times that I explain this again. Okay, perfect, thank you. So now we do not have classical superiorities with fermions, but I said before that we do have classical superiorities with scalars. You can do exactly the same, changing the formalism, and what you find is that you do not have now the same relationship as before with fermions. We have now a relationship, that relationship between the transmission coefficients and the reflection coefficients, okay? And what says there basically is that if omega and omega tilde have negative opposite signs, then we could have reflected radiation more emitted radiation than the incident radiation that we have. Okay, it's just because of the scalar field. Okay, mathematics are a bit different, and we have another relationship. Okay, so basically what that says is that we have classical superradiance for scalar fields, but in a very small range of frequencies, between minus QQ divided by R plus and 0. Okay, this is just for positive QQ, but for the other one it would be just the positive side. It's just for illustration. Okay, so the point is that in a very low interval of frequencies, we have excited modes, superradiant modes, that provide more reflected radiation than the incident radiation. Okay, that's for scalar fields. Now, more physically, in more physical terms, what happens is related to the weak energy condition and the area theory. You can, to explain classical superradiance in scalar fields, you need the area theory, classically. And the area theorem, for the area theorem, you need that the weak energy condition applies. So for scalars, everything is okay. For fermions, what happens is that the weak energy condition doesn't hold anymore, and then you cannot, the area theorem does not apply, and then it's not direct that you have superradiance. Actually, you can prove that you do not have classical superradiance. Okay? It's another way to see it. And now, I'm going to focus right now on quantum things. But for the classical part, let's analyze, before we go to the quantum aspect, let's analyze another choice of basis. We could have chosen this other basis, not the in-up basis, but the out and down basis. They are just the time reversed of the others, okay? It's just thinking in going backwards, basically. So out modes are just basically now, the Cauchy surface is not H minus and square minus, but H plus and square plus. Okay, so basically what we are having now for the out modes is just that we have going outwards, asymptotically far away from the horizon, a unit flux, and then we go backwards and recover that something has to come from the event horizon, transmitted, and something has been should have come from reflected. Okay, it's just going backwards with respect to the others. And for the down modes, they are just the time reverse of the up modes. Okay, everything works exactly in the same way. Okay, it's just so that you know that, because later we are going to do things with this other basics. Quantum.
Okay, so is it an assumption that it should be the same frequency as square minus and square plus, or it's something you can could something change the frequency in the process?
What do you mean is why we have omega and omega in the
where square minus is omega and square plus 2.
We should have omega in square plus and square minus, because basically the right wedge, you can see it analytically, but physically, you recover asymptotically Minkowski. And with Minkowski spacetime, what always happens is that the equations of motion, the solutions of the equations of motion are plane waves. And plane waves with the characteristic frequency of the system. And we have a charged black hole static with a characteristic frequency omega. So basically, this is what we expect. This is what it has to be. But also, of course, you can do calculations, and this is what it is. Okay, but everything is in the right wedge, in the square plus and the square minus, everything is Minkowski. Okay, and you can do the same with H plus and H minus, and you will find that you do not have omega, but you have omega tilde because of the scattering. Okay. Any other question or whatever? Quantum superradiance, which is my main focus. Okay, so we do not have classical superradiance with fermions, but do we have quantum superradiance with fermions? Do we have pair creation around the black hole? Well, for constructing a quantum theory, we need two elements. Well, actually one, but we can divide it in 2 steps. First of all, we need to choose a basis of solutions. That's why I presented to you before 2 bases of solutions. One with the in-up solutions and another with the out-down solutions. Okay, so first of all, The first step, we already have. Now, the second step that we need is a bit more bizarre, but it's not that difficult. What we need is to split the Hilbert space of solutions into two subsets. A one particle Hilbert space and a one antiparticle Hilbert space. What I mean is that we need to say, okay, this solution is going to behave like particles, and these solutions are going to behave like antiparticles. I'm going to say this with more detail, but that's the idea. It's not enough with choosing a basis of solutions. We need to do another choice. And I'm talking in terms of choices, and this is relevant. We need to choose what we call particles and what we call antiparticles. And it's a choice, because we have ambiguities in the choice of the quantum theory. Okay, and we are going to see this. Okay? So, what do we do in this example? What is the first thing that I would do? This thing. To canonically quantize, I'll choose a basis, the inner basis. Why? Because I want to. It's a choice. Okay? Let's analyze, later we'll analyze other choices, but let's first choose the in and out basis. So the in and out basis, I need to do the second step. The second step is, let's divide these enough solutions into what we are going to call particle states and antiparticle states. Okay? And how am I going to do this thing? And this is very relevant to understand everything. If we were in flat spacetime, this is quite easy. The thing that do everyone is the following: positive frequencies and negative frequencies. This is how everyone constructs a quantum field theory, not in curved spacetimes, but in flat spacetime. What people do, we have a static system like flat spacetime, and we say, okay, for all the in modes, for all the modes that behaved with the radial functions as before here, I mean, for the in solutions behaving like that, now we are going to divide the solutions into two subsets. The first subset is the ones that goes with omega positives. And the other subset, the one that goes with omega negatives. That's a first choice for the in modes. Omega positives are going to have positive energies, and they are going to be called particles, and omega negatives are going to have negative energies, which actually not, but I mean, for you to understand, they all have positive energies, but okay, just because they are, then we are going to do the complex conjugate, but I don't want to go to things that are unnecessary. But the point is, the first idea is that positive frequencies are related to particles, negative frequencies, antiparticles. Okay? And now, for the up modes, we could do exactly the same. But we are not going to do exactly the same. And this is a choice, because every choice makes sense here. Let's pick omega tilde positive and omega tilde negative. Okay? Why? Because now for the up modes, what is relevant is the H minus part. Okay? And the relevant frequency there is omega tilde and not omega. Omega tilde is not a frequency of the system. The frequency of the system is omega. Omega tilde was, I remember, omega plus a shift. Omega plus QQ time, divided by R plus. Okay? But we can, in principle, do this choice. And this is very motivated by what happens for scalars. For scalar fields, this is not a choice. This is what you need to do to have something. If not, you cannot construct a quantum theory. So basically, motivated by the scalar phase and motivated by the scalar case, I do this quantum theory, which I can because I can do whatever you want, following some rules, okay, that are followed. Okay? Any questions? Because this might be the most trickiest part. Perfect. So this is just a splitting of the solutions into what I call particles and antiparticles. So let's construct the quantum theory. Let's construct a quantum field operator. How do I construct a quantum field operator? I expand in my basis. I have some linear coefficients. The linear coefficients are annihilation and creation coefficients. I promote them to operators, annihilation and creation operators. And this is the expression that I have. Note that the pluses are related to particles and not and the negatives are related to antiparticles. Positive omega or positive omega tilde are related to particles. Negative omega or omega tilde are related to antiparticles. Okay, and that's how I construct my quantum theory. This is familiar to what you did in quantum field theory or what you usually do in quantum field theory. Okay, but now we are in a curved spacetimes and ambiguities arise and things change. But this is essentially what happens. Okay. Now, we've constructed a quantum field operator. We've constructed a set of annihilation and creation operators. And we've constructed a quantum vacuum. The quantum vacuum is a state that is annihilated by all the annihilation operators. Okay? So the quantum vacuum that we are going to call the in vacuum, this in vacuum has a physical property. And the physical property that it has is that it's empty in square minus. It doesn't have particles in square minus. Why? Because remember that the in modes behave like plane waves there. So it preserves what happens in Minkowski spacetime. And in Minkowski spacetime, you have one vacuum and that's it, that's all. I mean, in Minkowski spacetime, you define your Minkowski quantum vacuum that doesn't have any excitation. Doesn't have any excitation because it doesn't have any curvature. Nothing. I mean, you don't have an electric field, electromagnetic field, you don't have gravitational background that makes excitation of particles. Okay? So basically, we have chosen a vacuum that behaves as Minkowski vacuum, but only in square minus. Only asymptotically far away from the horizon in the asymptotic past. Okay? This is the in quantum vacuum. Any question? Because I think it's the most non-trivial part. Okay. This is one quantum vacuum. But we have infinite ones. Actually, okay? For example, the out quantum vacuum. Let's pick now not the in and out basis, but the out and down basis that I presented you before. Okay? And now what I do is exactly the same, divided into omega positives and omega negatives, so that I can define what is a particle and what is an antiparticle. Okay? What happens now, you remember? Well, now we have an out quantum vacuum. But remember that basically this choice is just the time reverse of the other one. So basically what we have now is that physically, this out quantum vacuum is empty, not in a square minus, but in a square plus. It's empty, it doesn't have particles, but only in a square plus. And yes, I'm meaning that particles are created in the other part of the Venn diagram. Okay? It's only empty in that way. Okay, so basically, what was our objective? Our objective was to discover that we have particle creation in this setting. And that we have, for example, if we compare a strategy to discover this, if we start with the in quantum vacuum and we compare it with the out quantum vacuum, the in quantum vacuum is empty in square minus. So if the in quantum vacuum, we find that it's not empty in a square plus, I mean, I do not have any incident radiation, but we have some particle creations. We have excitation of the field in a square plus. That would mean that the in quantum vacuum is not the same as the out quantum vacuum. Okay? So basically, quantum superiority is going to be, I start with the in quantum vacuum, and I find that the in quantum vacuum is not the same as the out quantum vacuum. Why? Because we have excitation of particles in a square plus. Okay? Any questions, please? Because if not, I'm going to. Should I say it again or something? So basically, the in quantum vacuum is not going to be the same as the out quantum vacuum. Okay? Why? Because we will have some particles here, and that's what I'm going to compute. What I'm going to compute is the difference between the out quantum vacuum and the in quantum vacuum. That's it. Okay? Okay, so let's.
So maybe it's just to understand, but It's just things come from H minus and
Sorry.
so here in is empty in square minus, but maybe not in H minus, so would that be relevant? If just these things, if some particles are just coming from H minus and go to square plus, then is it enough to call that superradiance?
Actually, that's what's happening. But the point is that that happens quantumly. Okay, your question is fantastic. Your question is fantastic because the in quantum vacuum is not static. It's representing a dynamic process. So in that sense, it's true that from H minus, we are having a flux going outwards to a square plus. But that's coming from the, we are going to see that. That's the reason why we have excitation of particles. I mean, those particles has to come from somewhere, yeah, from the horizon, I mean, from the black hole. So basically, what we are having is that if I'm an observer asymptotically far away from the horizon, what I see, what I feel is the in quantum vacuum. Okay? Now, that's in the past. Now, if I'm the same observer but looking back after, what I see is an excitation of my quantum vacuum due to a flux that is going outwards from the event horizon. This is the same flux that I showed you before here. I mean, wait, this one. I mean, here in H minus, we are going to have particles created that are going outwards. So basically, yes, we have a flux.
Maybe it's just a misconception from me. Somehow in my mind, it's different to have something coming from a white ball and something like a pair being created and being split, but maybe it's not different.
Maybe it's the same. I mean, and how do you call that?
I don't know. I mean, I'm trying to get a picture of it.
But that's quantum or just classical. Because classically, we do not have this with fermion fields. This is purely quantum. With bosons, we do have classical. Yeah. No, but I mean, I think your idea is what it is. So the summary and what we are going to do is basically compare the in quantum vacuum with respect to the out quantum vacuum. Okay? Now, how do we compute this? With this quantity. I don't know if this sounds familiar from your quantum field theory knowledge from flat spacetime. But I mean, what we do is to compare, you see, this out and down annihilation and creation operators with respect to the in quantum vacuum. This quantity is basic and summing to all modes. What we are doing is basically comparing the two quantizations, the two different choices. The one based with the out-down quantum vacuum, the out-down basis, and the in-up basis. We compare them. We compare them because of this, because we want to see that the in quantum vacuum is excited, it's being created particles in a square plus here, so that the out quantum vacuum is different from the in quantum vacuum. Okay? And this is giving us how it is excited, how much it is excited, how many particles and antiparticles are there, how much is the contents of the quantum creation. Okay? So what we find is that if this magnitude would be 0, then we wouldn't have any particles created because this is the number of particles created. But this magnitude is not 0. That's what we find. This particle is not 0 because we have particles and antiparticles created. Okay? So what happens is that this magnitude is not 0, just in a very, very low frequency interval, which is exactly the same low frequency interval as before, as in the classical counterpart for a scalar field. Do you remember? So basically, what we are having is that, okay, in summary, with fermion fields, we do not have classical superradiance. We do have classical superradiance with scalar fields. And for scalar fields, we have superradiance only in a very low frequency interval of frequencies, which is exactly the same interval of frequencies as here. So in summary, what matters is that we have, although the in quantum state is empty in square minus. It's full of particles in square plus because of low frequency modes becoming excited, because of the scattering potential of the black hole. That's the idea. The others are details. That's the idea, okay? And the contribution from modes is exactly the same interval of modes as in the scalar case, okay? Now, we can numerically compute the excitation of the modes. And what we find is this picture. So this figure makes sense because what says is that we only have excitation of particles for frequencies inside that interval. For omegas equal to 0, what we have is that the plane wave doesn't have enough energy to produce particles, to excitate the particles and create them, okay? But as we increase omega in absolute values, as we increase omega and we go in this way, particles are becoming excited. And of course, if we increase the charge, then if we increase the charge of the fermionic field, we increase the interaction, the electromagnetic interaction between the fermion field and the black hole, charged black hole. And what happens is that the interval is wider, and we have even more particles created. Okay, makes sense because the electromagnetic interaction is larger, and we can subtract more charge from the black hole. Okay. It doesn't go smoothly to 0 because it's sharply going to 0. We need widgets. This length. Okay. Perfect. Now we finished basically, but this is just to illustrate what's happening physically. We've just computed the number of particles created, but we can also compute other things. For example, the expectation values, the quantum expectation value of some operators to discover some observables. Okay, so the first observable, the quantum charge. Let's analyze what's the vacuum expectation value of the charge operator. Okay, and what we find is that, of course, we have an outward flux, as you said before, an outward flux coming from the event horizon. Okay, so basically we have, if the black hole is positively charged, we will have a positive outward flux of particles and a negative inward flux of particles. And then the positive charge of the black hole and the negative charge of the black hole, of the particles created, are going to annihilate and neutralize, basically. And that will lead to the discharge of the black hole. Okay? And this, okay, we can now analyze the energy loss of the black hole. How? Studying not the charge operator, the charge operator, but the stress energy momentum tensor operator. Okay, so basically what we study is, now that we have computing this quantity in the in vacuum and in the out vacuum and seeing that they are not the same because they are not the same quantum vacua, what we see is that we have negative energies in a region close to the event horizon, which is quite similar as what happens in curved black holes, in rotating black holes, very close to the horizon. And in that case, it's called an ergosphere, and here it's called an effective ergosphere. Doesn't have to do with the killings and vectors and so on. Here it's just because we have negative energies there. And because we have in a close region to the black hole, this pink region is the effective ergosphere. In that region, we have negative energies, and that's the reason why we can subtract energy from the black hole and emit energy in the form of pairs of particles created. Okay? So remember, quantum superiority is basically a loss of energy from the black hole and a loss of charge from a discharge of the black hole. Okay, and this is just a proof of it. Okay, and now, how much time do I have? Okay, a last comment. And that's a comment that can be very confusing. But this is basically a big part of my thesis and of my work. Okay? It's a study of quantum vacuum ambiguities in curved spacetimes. When we have very strong gravitational fields or very strong electromagnetic fields. Okay? So we've just analyzed this. We've seen that in contrast to what happens with Minkowski spacetime, where we have Minkowski quantum vacuum and that's it, and we have one quantum theory and that's it. Now, when we have these settings, we can have different quantum theories, and they can be relevant as well. I see this more or less like, of course, in classical mechanics, you can have different observers, an accelerated observer, or an observer going, I don't know. And each one of them are going to see different physics in the sense that they are going to experience different things. Of course, they are all correct, but their visions are a bit different in that sense. So each quantum theory adapts to a different situation, but they are all correct in that sense. Not all, if they preserve and they are sensitive, but everything that I'm talking to you about today, for me at least, on my research group seems sensitive, okay? But now, I propose to you two different quantum vacua. Let's propose another quantum vacuum. No, okay. Okay, I just remind here that I have to do two steps, choosing a basis of solutions and splitting the Hilbert space of solutions into positive and negative, into one particle Hilbert space and one antiparticle Hilbert space. The point is, other choices would lead to other annihilation and creation operators, other quantum vacua, and other physics. Yes. Do you remember the splitting of the modes that I said to you before? Okay, let's do another splitting. Let's pick, for example, this same splitting, omega positive and omega tilde, and omega negative, but, no, sorry, different thing, okay. I will have also explained it in that way, but here I choose another. So instead of choosing the inner basis or the outbound basis, I'm going to choose the in and out basis. They are not an orthonormal basis, but well, everything works fine if you do some changes, and that's what I refer to you here. Okay, so the point is, if I choose the in and out basis, what happens? What happens is that now this quantum vacuum, the quantum vacuum defined because of this choice, is going to be empty, asymptotically far away from the horizon, but both in stride minus and stride plus. What does that mean? That we do not have superradiance, quantum superradiance. And now you will say, and what are you telling me then? That's physics. Physics depends on the observer, basically. However, this quantum vacuum is a bit weird, and it doesn't behave well in the outer event horizon. Basically, this quantum vacuum is not properly defined. Actually, in the case of the scalar fields, in the case of the scalar fields, this cannot be defined. It's not that it doesn't behave great. It's just that it doesn't make sense. It breaks all the rules. But here, in the case of fermionic fields, we could in principle define them because we have more freedom in the quantization in the case of the fermionic fields, but it breaks in the outer event horizon. Okay, but yes, we have ambiguities in this sense. We could define in principle a quantum theory that is not compatible, it's compatible, but does not exhibit quantum superiority. Okay? Conclusions. Although a classical charged fermionic field on a charged black hole does not exhibit superradiance, we construct a quantum state that describes the discharge and the energy loss of the black hole. And this is a purely quantum phenomenon because we do not have the classical counterpart. And this differs from the scalar usual and standard field description. Okay? And this interpretation of this phenomenon depends on quantum vacuum ambiguities, as many other the Hawking effect, the Unruh effect, and all these quantum effects that are happening in quantum field in theory in of space times. I mean, this is not just for this particular specific topic. It just happens usually in quantum field theory of space times, provided that you break some symmetries in the system. Okay, and that's it. I think that I'm yeah.
Very much. So we have time for questions. Hi, sorry, I got late, so I didn't hear the first half. Sometimes scales. How long will it take to discharge a receivable fraction of your black hole? I assume it was the right loss for black hole.
No idea. No idea.
Would you estimate that? Would you estimate?
I should think about that. I mean, regarding the Hawking effect, actually, yeah, for the Hawking effect, which happens in the spatial black holes, I know that a lot of calculations have been done. So basically, it would, yeah, that's quite an interesting question. I think I should do that. I think it should be a analogous reasoning to those kind of effects, and we should find the answer to that. Yeah, but I haven't done it, so I cannot answer to you right now.
Well, and kind of related, although not completely. So one of the very interesting consequences of super radius is that it can be converted into sort of a runaway mode, and therefore it's
Sorry, I didn't.
into a runaway mode, and therefore the stability, for instance, if you have a master, so the 5 nodes get trapped, and they get further amplified, like the rest of also mirror kind of construction of black hole, right? But here, I mean, you just have black hole discharging, right? So it's kind of exciting, these sort of particle pairs, and in that sense, discharging. But these sounds, it cannot be transformed into sort of runway mode by stability. It's just a kind of smooth discharge, let's call it like that, of the black hole. So my question was if you would envisage a sort of more catastrophic process here, as you can do in classical.
Yeah, that was my point. That runaway solutions that are only classical. Yeah. So as here in this case, for
in classical field, any field that would have the classical situations, also have multiple situations.
Yes, yeah, for scalar fields, I think it's a quite different thing with respect to fermions. Because with fermions, we do not have classical superiority. So I expect, with my absolute ignorance, I would expect for our solutions that case, because that's classical, and I don't expect great things to happen there. But for scalar fields,
well, it's just that just because is it just because you for the bosonic fields you can have many particles in the same level of state, right? So that's how you build the classical state in a sense. But here you know, because they are from So is that simply the basis of the difference?
no, the difference basically is from the fact that that's what I don't know if you were here when I think it's okay. So the point is that for the scalar fields, it respects the weak energy condition. And the superiority, classical superiority comes from that fact. I mean, it comes from the area theory. And the area theory is written provided that the weak energy condition is satisfied.
Sure, actually, because let me consider the following. I consider a scalar field of actually kinetic. Actually, I consider a time coordinate field, but I change the sign of the kinetic term.
You change?
I change the sign of the kinetic, I make it into a ghost. Then it does not veil, weak energy condition. Yet, this is all linear, so the Klein-Gordon equation used to be the same solution.
That's true. What do you mean? Is that okay? Yeah, that's okay. Yeah, I understand what you say. I mean, it doesn't satisfy the weak energy condition, but we could proceed in the same way. And
The same description as in.
Yeah. Yeah, but I think that's not my implication. I mean, my implication is, if you have the weak energy condition, I can prove that you have the superiority. I'm not saying anything if you do not have the weak energy condition. Yeah, I mean, it could have seen, I mean, my idea was to say, okay, with fairness, you do not have the weak energy condition, and then we could interpret, I mean, it was just a motivation, but I'm not proving with that we do not have practical superiority with fairness. My proof was here. I mean, you need to do it. It was just a physical intuition, but of course, yeah, that's not a proof of it. The proof is if you have the weak energy condition, then you have. So,
Right, because I can build classical gradients from the field, which does not apply to weak energy condition. That's my point. I can see we get close to scale. So,
yeah,
but the fact that you have the classical gradients seems that it's interpreted sometimes in the literature as a fact that you can give the classical field with many particles in the same quantum state. So you can feel, yeah, the acoustics in this room.
Yeah.
This is an issue, but anyway, so you can build a classical field from many states and quantum states, well, many particles in the same quantum state. That you can do for bosonography, but you cannot do for fermionics. And hence you get a classical description, see? Because the Klein-Gordon equation is a quantum equation. But this, when we divide it, there's an H bar there, you know, it's like a Schrodinger equation.
Yeah.
But then it admits a classical description, but should only be legitimated when you have sufficiently large amplitude, which means many particles in the same quantum state, which you can do because it's a boson.
Yeah.
But of course, for fermions, you cannot. So, yeah.
Yeah, no, I think
That's what I'm saying.
I have one question also related to the discharge. So does it, I mean, if it's losing charge and then breaking this static assumption?
yeah,
So
perfect question. Perfect question, because the in and out quantum vacuum are not static, are dynamic. Are dynamic because we are breaking. It's a very nice question that I struggled with a lot. But now I think I have the answer. Where? Here. No. Where? Here, okay. The point is that because of this omega tilde, I mean, this in, out, quantum vacuum are not static. They are dynamic because of that omega tilde, okay? The static vacuum is the Goldberg vacuum that I showed before, in the last page, okay? That's compatible with this big system. But now, you might say, and why don't you choose a quantum vacuum that preserves the symmetry of the system? Because it could be preferred with respect to others. Completely fine with that answer. But with that question, the point is, first of all, the Goldberg vacuum, okay, but it breaks in the outside horizon. But that's not the answer. The answer is, for the Hawking radiation, for example, for studying the Hawking radiation, you can do two things. The other one doesn't matter right now. But the first thing is, okay, let's consider the spatial vacuum, which is also static, and then let's consider a quantum vacuum that is not static, because you could also define your Goldberg vacuum that is static. But you don't choose that quantum vacuum, you choose a dynamic quantum vacuum that doesn't preserve the staticity and it's called the Unruh quantum vacuum, and that Unruh quantum vacuum represents the dynamics of the dynamical collapse. So basically what I'm saying is that the Inner quantum vacuum here are also dynamical and are also hiding the dynamics of something that I cannot explain to you right now because I don't know and because I need to study. And this is one of the things that I want to study now. It's representing something, and I don't know if it's a dynamic collapse or something else. I don't know if it's hiding more effects such as the angle of the quantum variation that is related to dynamical collapse of a black hole or whatever. What is true is that I always have in mind that I'm working with a static resonance of black hole that has its limitations. I mean, static black holes. So these are results that are compatible with a lot of literature and that are not very crazy, but I mean, I'm still working with a static black hole.
Any other questions? Are there questions on Zoom?
No.
Okay. So if there are no more questions, I think we can stop here.